In this video, we're going to look at some examples of using trig substitution involving the tangent function. In this example, we want to evaluate the integral of 1 over x squared times the square root of x squared plus 4 dx. Because this integral contains an expression of the form square root of x squared plus 4, which of course is the square root of x squared plus 2 squared, we're going to make a trig substitution involving a tangent function. We do this because the expression under the square root is the variable squared plus a constant squared. And since that constant squared is 2, we're going to make the substitution x equals 2 tangent of theta. Well, once we choose x, we can write everything else in terms of x. Dx will be the derivative of that, which will be 2 secant squared of theta, d theta. We have an x squared in our integral, so we want to compute that, which will be 4 tangent squared of theta. And we also have the square root of x squared plus 4, which we can simplify by replacing the x with 2 tangent theta. And so we get 4 times tangent squared of theta plus 4 inside that square root. We can factor out a 4 from that expression, and we're left with tangent squared of theta plus 1. We know that tangent squared of theta plus 1 will be the secant squared of theta, so we get the square root of 4 secant squared theta. And taking the square root of that, we obtain that the square root of x squared plus 4 is equal to 2 times the secant of theta. We can now substitute all of these expressions back into our particular integral here. 2 secant theta can be substituted in for x squared plus 4 and the square root of x squared plus 4. X squared equals 4 tangent squared theta can be substituted in for x squared. And dx is 2 secant squared theta d theta, which we can substitute in for dx. And so making these 3 substitutions will produce an equivalent integral in terms of theta that we can then evaluate. So we start with our original integral, the integral of 1 over x squared, square root of x squared plus 4 dx, and make all these substitutions. So we have our x squared, which we can replace with 4 tangent squared of theta. We have our square root of x squared plus 4, which we can replace with 2 secant of theta. All of that's in our denominator. And then we multiply by dx, which we know is going to be 2 times the secant squared of theta d theta. We get several things to cancel here. We get the constants of 2's there will cancel. And our secant in the denominator will cancel with one of the secants in the numerator, although we still have another secant remaining there. And so when we get rid of all of the canceled terms, what we're left with is a constant of 1/4, which we can pull outside of our integral. We have a secant theta in the numerator, a tangent squared theta in the denominator, and then of course d theta. Now, in order to evaluate this integral in terms of theta, we have to do a little bit of rearranging. So for example, instead of dividing by tangent squared, we can think of that same integral as multiplying by the cotangent squared. So instead of having a tangent squared in the denominator, we'll move that term to the numerator, but we have to take the reciprocal of it, which is the cotangent squared. At this point, we can convert everything in terms of sines and cosines. So secant theta will be 1 over cosine theta, and cotangent squared theta will be cosine squared theta over sine squared theta. And we have a little bit of a cancellation here with the cosine theta. So what we're left with is the cosine of theta, a single power of cosine, divided by sine squared of theta d theta. Now at this point, this integral is much more computable because we can use a simple substitution. We can let u equal sine of theta, the inside function of the composition in the denominator, and then du will be the cosine of theta d theta. And so in terms of this substitution, this integral becomes 1/4. The integral of u to the negative second power, because that u squared is in the denominator, du. This is now a straightforward integral using the power rule. So continuing on with this calculation, an antiderivative of u to the negative second power would be negative u to the negative first power, of course, plus c. We can rewrite this a little bit by writing it as -1/4 times u. We can move that u to the denominator as long as we make the exponent positive, in this case positive 1. We can go back to theta by replacing u with sine of theta, so we get -1/4 sine theta plus c. And one last thing that we can do here is to make this a little bit cleaner. Instead of having a sine of theta in the denominator, instead of having a reciprocal of sine, we can simply make this -1/4 of the cosecant of theta. Now this step is not absolutely necessary, but in the very last part of this example, we're going to substitute a fraction in for that sine of theta, and so we want to try to simplify it a little bit if we can. And so rewriting a sine in the denominator as a cosecant is going to make our final answer look a little bit nicer and a little bit cleaner. And so we're going to have our integral being -1/4 times the cosecant of theta plus c. Our last step in this example is to go back to the variable x by using a reference triangle to determine the cosecant of theta. So we recall that our substitution that we used at the beginning was x equals 2 tangent of theta. Dividing both sides by 2, we see that x/2 will be the value for tangent theta, and we want to find the value for cosecant of theta. And so to do that, we use a right triangle. We want the tangent to be x/2, so the opposite side should be x, the adjacent side should be 2, and our hypotenuse is going to be x² plus 4, which we can find by using the Pythagorean theorem. And from this, we can find that the cosecant of theta is going to be the opposite, or the hypotenuse, square root of x² plus 4, divided by the opposite side, which is x. So cosecant theta will be the square root of x² plus 4 all over x. And we can substitute this back into our original integral here. And we have -1/4 times the cosecant, which we just said was the square root of x² plus 4 over x, all plus c. And so this is one expression for our particular integral. We have -1/4 times the quantity of square root x² plus 4 all over x plus our arbitrary constant c. If you'd like to try a similar example, you can pause the video and evaluate the integral of 1 over the square root of 100 plus x² dx. Resume the video, and in a few seconds, you'll see a detailed solution for this problem. Since the integral has an expression of the form square root 100 plus x², we can make the substitution x equals 10 tangent theta, and this will allow us to evaluate our integral appropriately. Once we have x, we know that dx will be the derivative, 10 secant squared theta d theta, and the square root of 100 plus x² can be simplified to 10 times the secant of theta by substituting 10 tangent theta in for x, factoring out 100, and replacing 1 plus tangent squared with secant squared, which is an equivalent trigonometric expression. And lastly, by taking the square root of the perfect square, 100 secant squared theta, to produce the 10 secant theta. Once we have all of these, we can substitute them into our original integral for dx and for the square root of 100 plus x², and we obtain the integral of 1 over 10 secant squared theta times 10 secant squared theta d theta. The constants of tens will cancel out. The secant theta in the denominator will cancel with one of the secants in the numerator, leaving just a single power of secant in our numerator, so our integral simplifies to the integral of secant theta d theta. We know an antiderivative for secant theta is the natural log of the absolute value of secant theta plus tangent theta plus c. And so to finish off our integral, we need to know the values for secant theta and tangent theta in terms of x, and then substitute those expressions in for secant theta and tangent theta, respectively. Well, we return to our substitution, x equals 10 tangent theta. Dividing both sides by 10, we see that x over 10 is equal to the tangent of x. And so that will allow us to replace tangent theta with x over 10. We then use those two values, x as the opposite side and 10 as the adjacent side, in our right triangle. We see that the hypotenuse by the Pythagorean theorem will be the square root of 100 plus x squared. And so from this triangle, we see that the secant of theta will be the hypotenuse, square root of 100 plus x squared, over the adjacent side of 10, which tells us that secant theta can be replaced with square root of 100 plus x squared all over 10, and this gives us our final value for our integral.